and welcome to part 2 of our Graph Gurus session. Today, we are going to be talking about something very important. We're going to be talking about converting a relational data set into a graph data set. This is important because for 99% of you coming into graph, your first graph is going to be doing exactly this. You're going to have a data set which you've been working with or which you want to work with. It's not going to be in a graph format, and you're going to want to work with it within a graph format. So we're going to take a look at what the process looks like, the thought process that is, in terms of understanding our data set, looking at the different concepts that make it up, and breaking out those concepts into things like vertices and edges that we will represent within our graph schema model. So for this session, there is some material available for you to follow along with. You can access this at this link, or I will post the link once again in the chat, just in case that doesn't show up for people who are joining new. So that link will bring you to this Google Doc, which will have links out to this presentation, TigerGraph Cloud, as well as the notebook/repo that we'll be working off of, and the data set and some additional information about it that we'll be using for this presentation. So I know the last presentation was kind of a follow along, do this along with me. This one will take a little bit less of a follow along approach. You're more than welcome to follow along. So if you head over to that GitHub link, that will bring you to this repo, which has some information in it, which I'll go over. But the main thing that you'll want to look at here is the notebook that we have in here. This notebook is essentially a notebook version of the presentation that I'll be going through, and it just has outlined explicitly in text all of the things that I'll be talking about during the presentation. So if you would like to follow along in a different way, you can go ahead and follow along with this notebook. This is also great if you need to refer back to things later on when coming in. Additionally, I will happily be answering questions through this. This is going to be a relatively dense, complex session, so I welcome questions wherever there may be, wherever you may have any. I'll try and do my best to keep up with the questions, but we're already going to be running a little bit tight on time. But I do want to help everyone understand exactly what we're going through, so I will be trying my best to get those questions answered as we go. So let's dive right into things. Today's goal will be to create a graph database schema from an existing relational database and understand the exact process of doing that. That's the important part. I don't care if we just get a relational database out of this. What I really want is everyone to understand the exact process that we're going through and start thinking with a graph mindset. The data set that we're going to be using for this is the United States Patent Office Patent Examination Research data set. So that is linked off with those links that I shared out, and we can see some more information about that data set if we head over to the link where it brings us to the data set. We'll get a little bit more into that as we go on, but if you just want to start exploring some information about that data set, then you can do that. There are 29 million patent applications in this data set, and patent applications are just one of the subsets that this data set talks about. So it's a relatively big data set, which is great. If last week was kind of a first introduction to graph, working with a tiny data set, this is the huge data set that will encompass all of the different pitfalls that you may run into when setting up your first graph. So while it may be complex, it's complex because it covers all of the different things that we could run into in a real world data set. So just want to make sure that we're covering all of our bases with that, even though it may have a little bit more upfront complexity. So before we dive in, I just want everyone to take a second and sort of reset their brains. I want you to leave what you know about relational data sets and how you structure them at the door. Don't forget it, certainly don't forget it, but check it at the door. We aren't really going to be using it that much in this, and it's better if we come at this with a fresh mind rather than trying to relate things back to the way that we've been doing them. So I ask that you do that. And then another thing that I want to say here, which may be very different from other types of databases that you've worked with, when we are designing our graph database schema, we do not care about our use case. So I want to say that again. our schema is independent of our use case. The schema reflects the data that we will be building the graph around. And later on, once we have that graph schema defined and we have that graph loaded, then we will write queries to suit our use case. So this graph schema that we're building is a representation of the data that we are going to be putting in our graph, not a representation of the use case that we are trying to solve for. So just let that sink in. I'm not even going to tell you the use case that we're building this graph for, not even going to tell it to you. That's how much it doesn't matter for this schema definition process. So like I said, the schema is based around the data. So first we have to understand our data. So we're working with this patent data set, and this patent data set is very large, like I said before. It's compressed on their website, but once you extract out the full data set, it's about 50 gigs worth of data. Depending on where you're coming from, large and 50 gigs worth of data may not be synonymous. I understand that. But what I want you to understand here is that if we're building this within Tiger Graph Cloud, or if we're building this within a cloud instance, then we need to upload 50 gigs of data. So just keep that in mind as we're going through this. And one of the things that we'll want to note about that is this data may not come out of that data set in a format that we want to load into the graph. So if we suddenly load in our 50 gigs of data and we realize that there's a column that's not formatted in a way that Tiger Graph likes, then we have to edit that data and re-upload it to our Tiger Graph server. And that's just a waste of time. So the first thing that we want to do with our data set is pare it down. So in the notebook, you'll see that I have a, just switch over to that. There's just a simple Python function here, which will take each of the 12 different files within our data set. And it's just going to create new files that consist only of the first 10,000 lines of each one of those files. So for each of our 12 files, this is going to spit out 12 new files, which only contain the first 10,000 rows from each one of those files. And what that's going to do is take our 50 gig data set and turn it into about a 10 megabyte data set, which is much easier to work with when we're trying to do some trial and error in terms of designing our schema. So that's just something you want to keep in mind whenever dealing with large data sets. I'm sure any data scientist watching this, it's just absolute, the default way to start off, but you want to pare down your data when you're doing these types of data explorations. That way you minimize the amount of time that you will waste having to re-upload or reformat data when you're working with it. All right, so that's our data. Now let's hop back into Graph World for a second with just a quick refresher on sort of what the anatomy of our graph and our graph schema looks like. So we have a vertex, which you may also hear me call a node at some point. The two words are interchangeable as far as I'll be using them, and a vertex is a representation of a particular data concept. I'm going to be using that phrase here a lot, data concept, and what I mean by that is a representation of something. So for example, a vertex could be a person. A person is a concept. That person has things about them that describe them, that have a name or other attributes about them. But overall, the person is a concept of which there may be other bits describing them. A receipt, you may purchase something and get a receipt in return. That receipt is a concept which can hold additional information about that purchase. House, same idea. Edges link together vertices via relationships. So edges describe how one concept relates to another concept. For example, if we had a vertex that was a person and a vertex that was a car, the person would own the vehicle. Person owns vehicle is the relationship between that person and that car. So that's the relationship that we're describing there. If we have two people, they can be friends. Person is friend with other person. That's the relationship that we are expressing via this edge. And additionally, attributes can be used to describe in more detail a vertex or an edge. So like I said before, a person might have a first name and a last name. That first name and last name are attributes that describe that person. So, they don't need to be, they're not going to be separate vertices. They're going to be a person vertex with a first name and last name attribute. Additionally, These attributes could go on edges as well. So say, for example, a person purchased something. Well, we could tie something like transaction date to that purchased edge. So person purchased item, but now that purchased item also says the date in which that person purchased the item. So now we can traverse that edge, and in the process of traversing that person purchased item edge, we can pick up that transaction date from the purchased item edge. So that's kind of the anatomy. But in order to fully understand and to fully allow us to build the most efficient schema, we have to understand how Tiger Graph deals with those different types of vertices, edges, and attributes. So first off, everything is stored on disk. All of your graph is stored on the disk of the Tiger Graph server. And then once you start up the Tiger Graph server, certain aspects of that data are loaded into memory, where it can be more quickly accessed. The things that are loaded into memory are the primary ID of all of your vertices and the edges between them. So essentially, a vertex exists in runtime as a memory location, and an edge exists as a pointer between two memory locations. So whenever you want to traverse an edge, you're simply jumping between two different memory locations, and that is extremely fast. Attributes, however, do not get loaded into memory, because that would just take up a lot of memory, and we don't really need that. So when you reference an attribute, there are exceptions here. These are all general rules. I just want to put these out here for understanding. There's obviously more nuances, but when you access an attribute, you're pulling it off the disk. You're reading it from the disk. And because of that, accessing an attribute will always be slower than traversing an edge. So just keep that in mind. Right now, I just want you to keep that in mind. We'll dive a bit more into that as we explain some of the choices that we make in our schema design, but just keep that in mind that traversals, so going from one vertex to another vertex via an edge, are extremely fast and computationally cheap, whereas accessing an attribute is less performant. So let's dive back into our data set. We'll be looking at the PATX research data set. There are, like I said, 12 unique files, and we're going to be going through each one of those files and breaking out the different concepts that they talk about. So while these files do represent the tables from a relational database, within each one of those tables, it may be talking about more than one unique data concept. And because of that, we need to be able to recognize those different data concepts so we can break them out into the vertices of our graph. Now, one of the great things about this data set, and anyone who's dealt with real world data sets, I'm sure can feel pain from this experience, but this data set has a fantastic documentation. So there is a great appendix describing the entirety of the data set, going through each and every file that is in the data set, talking about exactly what each field means, the quantity of each field, and breaking it down into the data type of each field for any given file within our data set. So this is linked in that link set, and you can also get it from our data set page if you merely click on the appendix link here. So that's going to be very helpful, something you want to keep open when you're exploring your data set. Something that I should mention is that you need to understand your data set in order to create a schema for it. If you do not understand the relationships that your data inherently has, then you're not going to be able to create them in your graph schema. And if you can't accurately describe your data, then graph really isn't going to help you as much as you would hope, because you fully don't understand the connections in the data. So therefore, the graph's not going to be able to fully understand the connections in the data, and you're not going to be able to get the best output out of that graph. All right, so that's a lot of talk. Let's jump into hopefully the fun stuff, and let's start looking at our data files and what we need to keep in mind when building our schema. So we're starting with our first file, which is allinventors.csv. As the name implies, this contains information about inventors. So one thing I want to say here, that even though this table is kind of split up into two different sections, that is purely for display purposes. So this is all, imagine this is all one wide table. I've just split it into these separate rows for the sake of fitting it on a slide in a way that is actually readable. So all of this is the All Inventors table. And in the top, we can see our column names. And below that, we have an example row of data. So we can start looking through this and we can see that this isn't just talking about inventors. We have application number, which corresponds to our patent application. And then we have these rows here for describing our inventor: inventor city, inventor region, inventor code, inventor rank, and then inventor name. But while these do say inventor, they're not all describing an inventor. So if we take a look at this, application number, this is describing our application. So our data set consists of patent applications. So that's what this is referencing to. This is referencing our inventor that we're talking about back to an existing patent application. And then here, inventor first, middle, and last name, well, that's pretty easy. Those describe our inventor. Inventor rank. So this is where our knowledge of our data set comes in. Once again, this is the kind of thing you want to have Google open while you're looking for your data set. You want to have that appendix open while you're going through your data set, because looking at inventor rank, I don't necessarily know what that means. I mean, I do now, because obviously I went through this data set, but this inventor rank corresponds to an inventor's rank on an application. So the order that the names are in an invention application is their rank. So the name that happens to appear first on the application is rank 1, second, rank 2, so on and so forth. Now this seems, this is interesting to us. This is something we want to keep in mind because maybe we want to take a look at, the average rank of an inventor on applications. So that's not something that necessarily refers directly to an inventor because they have that rank for a given application. So this is a separate concept that we want to look at. And then additionally, down here, these, while they do say inventor in front of them, city, region, country, those don't really describe an inventor, those describe a location. So we want to take a look at those as location attributes or location vertices rather than an inventor vertex. And I'll break that down in this next line here. So there are two different ways that we could save this. We could save this entire thing as a vertex. So this could be a location vertex, and it could have the attribute of country, it could have an attribute of region, and it could have an attribute of city. That's fine. Or what we could do is we could break off each one of these into its own vertex. So we could have a vertex labeled city, a vertex labeled region, and a vertex labeled country. But why would we want to do that? What would be the best way to do that? Well, it comes down to the way the graph works. But essentially, I can boil it down to this. If you would want to filter on something in the future, then it should be a vertex. So for example, if I wanted to select all inventors who are in California who have region code CA, that is a filtering operation. I want to filter on that region code. So therefore, region should be a vertex. Now I'm going to explain that because that may sound a little confusing at first. So we're going to walk through a theoretical scenario here. I want to find all inventors who are from the city of Boston. Okay, so with city as an attribute, so let's say city is an attribute of inventor. So we have an inventor, we have attributes of their name, and we have attributes of the different aspects of their location. So if city is an attribute of inventor, then in order to get all inventors who are in the city of Boston, I have to select every single inventor in our database. I have to now read the city attribute, which is hitting the disk. So this is a slightly slower operation. I have to compare the value that I get from that attribute to our input value of Boston. And then from there, I can return any inventors who match that value. Overall, through this process, we are touching every single inventor vertex in the graph. So for this data set, we are touching 21.6 million vertices just to return a couple thousand inventors who live in Boston. Now, conversely, let's look at this as if city were a vertex that was connected to inventor. So we have an inventor and they live in a city. So live in is an edge that connects this inventor to the city vertex. So what we will do is we will select the vertex Boston because Boston is one of our cities. So therefore it has a unique Boston vertex for it. And then from that Boston vertex, we can just grab all of the edges, all of the from city edges that connect to that vertex. Because if you remember, our inventors are tied to a city. So any inventors from Boston will be tied to the Boston vertex via the from city edge. And then from there, we can just return any inventors that have a from city edge connecting them to Boston. And what this means is we select our Boston vertex, and then we traverse those from city edges, which only lead to inventors from Boston, and then we return those inventors from Boston. So the number of vertices that we touch in this operation is the number of inventors from Boston plus the Boston vertex. So instead of going through our entire database and checking every single vertex, we only ever touch the vertices that we actually want to return. So if we look at these numbers here, instead of hitting 21.6 million vertices to find all of the inventors from Boston, we just hit the 1,700 inventors who are from Boston. So this is a huge performance increase, and this is why you want to separate out anything that you plan to filter on as its own vertex, because then when you go to filter on it, instead of having to go through the whole graph and check these values, you can just traverse those edges, connecting that filter vertex to what you're trying to select. So this is what that looks like. Here we have an inventor. Here we see they are from a city, they are from a region, and they are from a country. Those are these locations that we described before. But you'll see here that we also have these edges here in region and in country. And you'll think, well, where are we getting that information from? And that's actually pretty interesting because we can infer that information. So we know that country is our largest subset. Regions are within a country. So in this case, a region code is our state code, and then a city is within a state. So already just from this one row of data, we know that Sonoma is a city in the region of California, and California is within the country of the United States. So we can easily assume those edges because we now know that. So instead of just having our inventor tied to a city, tied to a region, tied to a country, we now know the city is within this region is within this country. And this is going to help us build a more dense graph and better understand our data as we go through. And additionally, it will allow us to now be able to query on different things. So before we could say, find me all inventors within this region, now I can say, find me all regions within this country. Something we couldn't do if we had just tied our inventor to those particular location vertices. So that's our first data file. That was pretty quick. I know we kind of covered a bit there. So that was our all inventors file. So let's move on to our next one, which is, sorry, this is just kind of showing, okay. So this is still our all inventors file. And if you remember before, I talked about rank. So with what I said before about rank is something that we potentially might want to filter on. You know, I want to find all inventors who have been ranked 1 on a patent. Okay, well, with what I said before, that would mean that we would break out rank into its own vertex type. Now, unfortunately, this isn't going to work for us, and I'm going to explain why. Just, I want you to follow along with me, because when I see a lot of people coming into graph, this is the way that they kind of think of things. And I want to walk through that thought process of how people usually think about things and then describe why that's not the way to think about things, and then present, you know, the way that we should be doing this. So I want you to just bear with me as a sec as we walk through this. So rank is something we want to potentially filter on. So we have a question here. Boston implies there's only one instance of Boston as a region vertex. Is that a function of loading the data? So there can only be one of any vertex with a given ID. So say we load in a data and we have 30 inventors who are from Boston. They have that city, Boston. For each one of those, when we go to load in city Boston, the first one will say, okay, city Boston does not exist, so we will create the vertex city Boston. The next person who goes to load in will say, all right, we've loaded in the inventor. let's connect them via an edge to a vertex, and it'll say city Boston, and it'll say, okay, city Boston already exists in our graph, so we're going to just connect them to that existing vertex. So as long as the ID is the same, so Boston is the same across that vertex type, then any subsequent inventors who get loaded in, who have the value of Boston as their city, will be connected to that existing Boston city vertex. Hopefully that was able to answer the question. Getting back to this though, we've broken out rank as its own vertex because we want to filter on it, right? And we have application here. So now let's look at a theoretical scenario where we want to find out what rank an inventor is on an application. So we have an inventor, they have a rank vertex, there's a rank vertex, inventor has rank, saying that they are a rank, and inventor filed application connected to an application. This seems good in concept. So now let's take a look at it if we think that that inventor has filed multiple patents or multiple applications. So we have application 1, where they have rank 1, and we have application 2, where this inventor is rank 2 on application 2. So if I wanted to say what rank is inventor, then that would return both rank 1 and rank 2, because that inventor is connected via the has rank edge to both of those ranks. I have no way of telling which application rank 1 applies to or which application rank 2 applies to. So okay, that's fine. So we can add another edge in here, right? We can say inventor filed application 1. Application 1 has inventor rank 1, and our inventor also has rank 1. So we have this nice little triangle here that we can sort of traverse. We can say, find me application 1 and find me the inventor's rank, and see if they have that rank on application 1. And that seems like it would work, right? You know, we have application 1, we have the rank, and we have a way of tying rank 1 back to application 1. However, this issue comes in when we start thinking about our data set as a whole. So if you think about it, every application is going to have a rank 1, because rank 1 is the first name on the application, and you can't submit an application without having a name on it. So now if we look at this, application 2 will also be tied to rank 1, and there could be some other separate inventor that is rank 1 on application 2. So now if we want to say, find out what rank our inventor is on application 1 and application 2, we would say, okay, find the applications that inventor has filed. So that's going to return back application 1 and application 2. And then we're going to say, find the inventor rank for those applications. And for application 1, that'll return rank 1. And for application 2, though, that will return both rank 1 and rank 2, because, you know, it has rank 1, it has to, and our inventor is rank 2 on that one. And then we can tie back from those, and we can see that our inventor has rank 1 and has rank 2. And now we're in the exact same spot that we started in, where we know the ranks that our inventor has, we know the ranks that our application has, but we have no way to tie those ranks back to our inventor in the context of that application. So I know what you're saying. Well, you just told me to break out anything that I want to filter by into a vertex, and now you're telling me that that's not going to work for this particular situation. And that's right, because the thing that we need to realize here is that that rank does not apply just to the inventor. That rank is a product of the inventor and the application. You know, before, when it was something like city, that just applied to the person. Person is in city. That city doesn't have any additional relationship there. However, this rank, inventor has rank within the context of this application. So we have to keep track of these two, inventor and application, as well as that rank that connects them. Well, what is something that connects two things in the context of our graph? Well, that's just an edge. So therefore, it makes sense for rank to be an attribute of an edge, because the edge already describes the relationship between that inventor and that application. And what does the rank do but add additional information to that relationship? So now, instead of having a separate rank vertex, we can store rank as an attribute as the edge and say inventor filed application with rank 1, and then the application that they filed. So we link our inventor to their application, and now we have that rank, which describes their rank for that specific application. So while we do not get the performance boost that we could have gotten by having that be a vertex of rank, a vertex of rank also just wouldn't have worked within the context of our graph schema. So we're not losing out on performance if it wouldn't have worked at all in the first place. That's just something to keep in mind as we think about these things. So we can see what that looks like if we have multiple applications. Once again, we can now clearly see Inventor has rank 1 for application run, and they have rank 2 for application 2. So that is how we want to describe these things like rank, which relate to more than one concept. The rank on its own means nothing, but the rank in context of the inventor and the application means something. So therefore, it has to live on an edge. So let's look at our schema so far. We have an inventor. They're from a city. That city, they're also from a region, and they're from a country. And those can all be nested within each other, like we talked about. And then those are also tied to an application. I see the comments now. I understand the question saying that there can be multiple cities named Boston, and that's entirely true. So maybe instead of using Boston as the unique identifier here, you want to use Boston plus region. Boston MA is going to be Boston, Massachusetts, where you might have Boston in another city. So poor example on my part, but this is something that you can overcome with the graph by simply, and we'll actually talk about this later. So I'll bring this up later. I want to keep things simple as we start off, but I will get into how we could deal with that type of scenario later on. And that relates back to this. Inventor needs a unique ID. Every vertex needs a unique ID. For vertices that don't have attributes, we can just use the value that we're storing as that unique ID. For example, country. Country codes, country, if we look at our appendix, country are ISO codes. So these are guaranteed to be unique. So therefore, we can use them as a primary identifier. So this vertex, the primary ID of country, would just be the value of that country code. However, with Inventor, we need to have a primary ID so we can tell that inventor apart from other inventors. And if we look back at our inventor file here, none of these fields are a unique identifier. So what do we do there? And we'll get to that. I want you to be thinking about that right now. We'll get into it as it makes sense, but just know that for a vertex to exist, it has to have a unique ID. And if we don't have a unique ID in the data set that describes that vertex, then there's some stuff that we can do in order to generate one. But we'll get into that later on in the presentation. So this is what we're dealing with our schema so far. So let's take a look at some more files. Transactions describes events that happen over the course of a patent application. So if we see here, it has an application number, an event code, and a recorded date. So these events take place and they have a date that they happen on, and those events tie back to an application. Now, again, there's a couple different ways that we can model this. There's plenty of ways to do things in graph. There's no right answers, but there are plenty of suboptimal answers. So I just want to go through some of those options and let you know why they may not be the best choice for the given scenario that you're working with. So here we'll look at two different ways in which we can express that relationship of having a event code tied to an application. So first we can have our application, which then has something called a transaction. That transaction stores the date that the transaction took place on, and that transaction also has an event code tied to it, which describes the type of event that was. This will work, but it's going to present us with some interesting things that we'll have to overcome. First, anytime we want to get the full list of event codes from an application, we have to now traverse two edges. We have to go from application to transaction, and then from transaction to event code in order to return all of the event codes for any one application. And that's okay, it will work, but we're traversing two edges. Additionally, this transaction concept here isn't really something that exists within this data set. We have event codes that exist, we have a recorded date that exists, and while all of this together can be considered a transaction, that's not really something we care about in a way, and I'll get to that, because there's no primary identifier for it. There's nothing that says, here's the identifier for this specific transaction, and here's the information that relates to that transaction. So in order to do this, we would be traversing 2 edges to get our event code, and we have to generate unique IDs for each one of those transactions. Now, if we look at this other way of expressing our data, we have an application, we have a code, and then we have a vertex of event code. And then along the edge of has code, we have that date attribute. So application has code, event code, and we can see that it received that event code on the date that is stored as the attribute on that edge. So now when we want to get all event codes for an application, it's only one edge traversal, and the event code itself serves as the unique identifier for our event code vertices. So therefore, we don't have to generate that, and we can easily add this to our schema without having to worry about the extra bloat of generating a transaction vertex and having an extra edge in there. There's a question about directed and undirected edges. I will cover on that. For the most part, although I apologize, all of these drawings have arrows in them just because that's how they were drawing. But it is, none of these edges are required to be directed. I'll talk about ones that are, we'll get to that, I swear, and I'll bring that up. But for the purpose of all the edges that we've been through so far, they do not need to be directed. These could be undirected edges because they merely describe this relationship between inventor and application, or inventor and rank, and so on. Because we are talking about 2 different vertices, the ability to, the directionality is not necessary because we can always go from inventor to rank or rank to inventor. Like I said, I'll talk about when directed edges are important in a little bit, but for now, you can assume that all of the edges that we're creating are undirected. However, they will function just the same if they are directed or undirected. So we covered over transactions. Event codes, this one is very simple. We just contain an event code and its description. And really all we're going to do with that is just add that description to our existing event code vertex. So now when we pull up an event code, it will have an attribute, which is a human readable description instead of just a string of numbers. So this will just help us as we're going through our graph and we're looking at these event codes, we'll be able to query and see what those event codes are actually describing instead of just seeing that number and trying to figure out what that represents. Our next file is attorney agent. So for every patent application, there is an attorney associated with it, at least one. And if we look at this, we can see that there are a couple different concepts that we're talking about here. So the easy one is our attorney. We have things describing our attorney: first, last, middle, suffix, phone number, registration number. These are all values of our attorney. Additionally, attorney practice category. This could be used to describe our attorney, but this is also something that we might want to filter on. So therefore, we want to break it out as its own vertex, because these practice categories, say I want to find all attorneys who are of a certain practice category. Now I can just select the vertex for that category and then easily traverse out to the attorneys connected to it. So we'll want to break that out into its own vertex. And then once again, our good friend application number describes the application that this attorney is related to. There's a question, is the label of an edge its identifier? It is not. An edge is defined, the identifier of an edge comes from the primary ID of the vertex that it is coming from, and plus the type of edge, plus the primary ID of the vertex that it is going to. And I'll talk about this a little bit more. Y'all asking questions that I swear I'm going to get to. It's like you're reading ahead in my presentation or something, but we're going to get there and everything will get explained. So let's take a look at our schema so far now that we've added in attorney and practice. So we have our inventor and our locations that we've talked about already. We have them filing the application and we have the rank along that application edge. Our application has codes which occur on a date, and those codes have a description. Then an application has an attorney with all these attributes describing the attorney, as well as that attorney having a practice category. And that practice category is its own vertex, so we can use it later on for more efficient filtering. Now it's time for the big one. So there is one file in this data set that contains all of the information about applications, and this is the big one that we're going to be breaking down. Look at all these colors. So there's a lot that's being talked about here. I'm going to jump through this because there is a lot more that I want to cover, and we are starting to run out of time. But what we can see here from these different colors, although there are a lot of them, is that we are describing an application, which has an application number, a filing date. Looking at, we also have these two confirmation number and docket number. Looking at the appendix of our data set, we can tell that these are numbers used for external reference. So they're not anything we want to filter on. They just describe the application. So because of that, we're not breaking them off into their own vertices. However, something like application invention type, well, we might want to filter on the type of the application that we're filing. So therefore, that's its own vertex. Examiner full name. Well, an examiner is not an application. So therefore, it's a separate concept from application, which means that it's going to be its own vertex. Examiner art unit. Well, we can assume, again, that that's not an application because it doesn't say application. And once again, reading through that appendix of our data, we know that the examiner art unit is the unit that a particular examiner belongs to. So once again, this is something we might want to filter on, find all examiners from a specific unit. So that's its own vertex, and that will be tied to our examiner. USPC class and USPC subclass. Again, these are things that describe our application, and they are things that we might want to filter on. Find all applications of this class, find all applications of this subclass. So they're their own vertices. Confirmation number and docket number we talked about. Status description and status date. Status description is something we might want to filter on, and status date is something that we need to convey in the edge that connects application to the status. An application can have multiple statuses. Those statuses can change over time. So in order to maintain all of those statuses over time, we need to store that date along the edge of our application status description. File location and file location date are exactly the same mindset as status description. They are things that we might want to filter on, and then the date that we want to keep track of for that edge that links those together. I like this question. The question about, we're talking about we want to filter on these things, and you're saying, we know we want to filter on them because of use case. But the thing here is we're not thinking about a specific use case. We're thinking about all use cases. So we're not just saying, I want to filter on this because I think it might be interesting in the future. We're saying, I want to filter this because this is something that describes a unique aspect that is shared by other pieces of the data. So if you can think about it this way, anything that is going to be any attribute that will be unique for each vertex should be an attribute. So for example, when we were talking before about attorney, the full name of the attorney or the phone number of the attorney is going to be unique for each attorney. No two attorneys hopefully will have the same phone number. So therefore, that's going to be unique to that attorney. However, if we had something like file location, well, the file location is the location where the physical files of the patent application are stored. There's only a couple file locations across all of our applications. So therefore, it doesn't make sense to include it as an attribute because there's maybe only 3 or 4 file locations. And because of that, we can filter on it. It's not a unique value specifically describing that application. It is its own concept, which is tied to an application. So when I say filter, I guess really what I mean is whether or not it has a unique value related to that one specific instance of a vertex. Our status descriptions are going to be a bunch of applications with the same status description. So therefore, it's something that makes sense for us to peel off of our application instead of storing in there. The rest of these PJOB number and WIPO number, these once again are more patent related things, but if you read into it, they follow along that same idea as our status and the date where we want to store them separately, and then have that date tied to them as well. Patent number, again, an application can result hopefully in a patent. So we need to store that as a separate thing because the patent is unique from the application. So it should be its own vertex, it's its own concept. Invention title, that will be unique for each application. You know, you're not going to submit two separate applications with the same title. So therefore, this makes sense to be an attribute because the title is so closely tied to the actual application. These last two indicators are exactly that. They're just things that we can filter on. So looking at what this looks like as a schema in kind of this graph form that we have before, we can see now that we have sort of this spider web pattern. We have a central application node, and we have a bunch of other vertices attached to it that describe that node. We can see some of those contain a date where it is relevant, and others, like our examiner, have attributes, and then they have these other things like the examiner unit branching off from it. Foreign patents, this is, once again, we can see here that we are linking a patent to a foreign patent. So say I want to reference a patent that was filed in France with the patent that I'm currently filing in the US. I need to reference that foreign patent. So this will tie us back. One thing to note here, patent country. Where have we seen that before? We already have a country vertex. So what we can do, here's our foreign patent here, we can tie that to the country vertex that already exists. Because as long as our data follows the same format, which if we check the appendix, we know that the country here will follow the same country code as it does with our inventor location, then we know that we can tie our foreign parent patent to the same country vertices that we've created before. So now we've enriched our graph with some more information. So not only do we know now the application has a foreign parent patent, but we know the country that that foreign parent patent is from. And because we have this other information, we now have information on that foreign parent patent's country in relation to other countries or regions where our inventors may be located. So we've gained this new insight into our data set because we were able to piggyback off of this existing vertex type. Patent term adjustments is this file. And as we see here, we kind of have this big PTA event, which is a patent term adjustment event. So something that affects how long the patent is going to take to file. And then we also have this indicator here, which we've chosen to break off into its own vertex because this, again, follows kind of that same filtering logic as before. Was the application actually extended or was it not? That's something that we may wish to think about as we go further down the line. So breaking this out, this is where we start to see something a little funky. And this is where I'll talk about directed and non-directed edges. When you need to maintain hierarchy, you need a directed edge. If you don't need to maintain hierarchy, you do not need a directed edge. So for example, PTA event to application. There isn't really a hierarchy there. You know, we know the application is where we want to start and we know the PTA event is where we want to end, but there isn't really any dedicated hierarchy there, so we could get away with an undirected edge. However, these PTA events, they have this start sequence number. So basically what this means, again, this is our background patent knowledge, events can spawn other events. So one of these PTA events could happen, and as a result of that event happening, it creates another event. And this PTA sequence number, start PTA sequence number, will take that second event that was created and that will relate it back to that first event and say, this event caused this event to happen. And that's what this has start edges here. But because that PTA event has start edge points from one PTA event to another PTA event, there is inherently a hierarchy there. One of these was the start event that the other event was spawned off of because of that. So because of that, our start event has the hierarchy. We need to know which order that edge goes in. So therefore, it is necessary to have a directed edge in this case to say, this event started this event. If it's not directed, then we just see that those two edges are connected and we don't know which one was the start event and which one is the resulting event. Then additionally, we can just see our extension indicator, and the rest of this looks like some of the schema stuff that we have gone through before. So the thing to note here, and the big thing I want to get to really quickly then, directed event is a chain, more or less, yes, it is a chain of events. So the main thing I want to get to here, PTA event does not have a primary ID. If we look at this, we have no unique way of representing a unique PTA event. Because of that, we need to generate a primary ID. And there are two ways, well, there are more than two ways, but I'm going to talk about two ways in which we can do this. So within TigerGraph, we have these things called token functions, and these are essentially functions that run when your data is being loaded. So these can do things like convert strings to lowercase, to uppercase. They can convert different data types, string to int, string to date time. Whatever you're trying to do, just some of your basic data processing that you might do outside of your database, you can now do as you're loading your data in, and it just helps it make it easier to bring files directly into TigerGraph without having to augment them first. One of these token functions is gsql concat. And what this allows you to do is concatenate multiple different columns into one entry. For example, this is not the best real world example, but I want to show this here. With our patent term adjustment, like I said, we don't have a unique identifier. Say, for example, we could only have one PTA event per day per patent application, okay? So if we're only allowed to have one PTA event per day per patent application, then a concatenation of the application number and the date would result in a unique identifier for that event, because each application could only have one event per day. So therefore, combining the application with the date will give us a unique identifier. In the real world use case for this data set, that is not the fact. We can have multiple events on the same day. So then in that case, bringing in something like the event description as well. So now our unique identifier for this particular PTA event is the application number plus the date plus the description. That might be unique. For this case scenario, this is not a good idea. Obviously, you can kind of see why that's not the best, but in a simpler use case, say we are modeling a deck of cards, we have two columns for suit and one for value. We have 4 different suits, we have 13 different values. So therefore, neither of those is really a unique identifier, because for any suit, we can have 13 cards within that suit. And for any card, we can have 4 different suits of that card. But there is only one of each type of card per suit. So if we were to concatenate together, 4 of hearts, now we have a unique identifier versus just 4 or just hearts. For our data, our use case, this doesn't make sense. But if you want to generate a more human readable primary ID, gsql concat can be an interesting way to do it based on your data set. For us, because of just the sheer number of possibilities, we want a truly unique ID, and we have a token function for that as well. So UUID v4 will generate a guaranteed unique ID for that vertex. It's just a big string of random numbers and letters, so it's not the most human readable, but it is guaranteed to be unique. So these are just some different trade-offs that you can think about when looking at your data set and trying to generate primary IDs if you need to. I'm going to breeze through these ones really quick. PTA and PTE summary. Just like we had those PTA events, the summary is the combination of all those events. So each event can impart a delay on the patent. These summaries just describe the overall delay that a patent has experienced during its lifetime. And we can see these described in this right section here. where we have PTE Summary, PTA Summary, and then we've also added in our PTA event chain and the extension indicators along with it as well. So we can already see that our graph is starting to get more and more complex as we go. This is the last one I'll really cover through. There's some more that we can skip through, but continuity children, so you can continue a patent, allowing you to make changes to it, allowing you to break chunks off of it, to modify it, all these different sorts of things. And the relationship of these continuation patents is described by continuity children and continuity parents. So that just has the application, the child application, and the date. And we can see that we can describe that much like this. So once again, we have a directed edge case here because we have that natural has parent, has child is like a textbook hierarchical graph example. So our application has a child application. It's directed because there is a parent and there's a child. And then we have the date of which that relationship was established. So that's an attribute of our edge because it's describing the relationship between those two applications. Additionally, continuation type just describes the type of continuation that we're doing. Like I said, there's all sorts of different ways that you can continue a patent. And because those are a subset of unique concepts, we want to create a vertex for that as well. Lastly, this is our last one, correspondence address. We can see how that's broken out here. Basically, for each patent, you have to have a way of getting in contact with the person who filed the patent. So this just does that. And we can see what that looks like when we bring it together. That's the lower half of this before. We can tie our correspondent to the postal code, which we were able to grab from here. And then all of this links back to those city, region, and country vertices that we've already created. We can add some additional edges in here as well to connect our address and our postal code back to city, country, and region. And that creates this nice, dense, connected location area of our graph. And this is what everything looks like all together. This is that patent data set that we just went through. This is all 12 files sort of organized as a schema based on the different concepts that they represent, the attributes that describe those concepts, and the relationships between those different concepts. So I'm sure I'm already over time. I knew that that was going to be a tough one with this. I would have loved to have more time for questions, but we do have plenty of ways for you to get in contact with me to ask questions. You can either do it through our community forum, community.tigergraph.com. Feel free to ask questions there, or through our developer Discord page. Shoot me a message on LinkedIn, really however you want to get in contact if you have any questions about this. I'm going to scroll through the list really quickly, hopefully see if there's anything that I could quickly answer for any of these. So back before when we were talking about, where was it? We needed to generate unique IDs. I believe at the very beginning, we talked about this unique ID for our inventor, because we don't have a unique inventor ID. We could either use that UUID function that we talked about before, or something that could be interesting. And this may or may not work for our data set. Like I said, this is why we load in those smaller files to play around with things before we load in our full data set. We could do a concatenation of first name, middle name, and last name as a unique identifier. This may not be unique across our data set. That's something we'll want to explore. But what this will do is ensure that if one inventor has filed multiple patents, then all those patents link back to that same inventor instance, as long as the inventor used the same name for all of those patents. So the conversion only looks at tables, fields, but not looking at the relationships from the database. So you need to design the edges from scratch. So this concept that we're looking at is doing all of this by hand. We are taking that those CSV files, we are manually going through them, and we are building out the schema based off of that. We do have built into TigerGraph, we do have a way to import a relational database, and it will attempt to build a schema off of that. I don't have the most experience with that functionality, but that may be more along the lines of what you're talking about, where it would be able to automatically generate the schema for you or assume some of those relationships. So yeah, that was extremely dense. I hope everyone was able to follow along there, and I'm sure there are plenty of questions and things that I can help clarify. So I do really hope that people reach out and ask if you have any questions, and I would love to be able to make this presentation better, hopefully, so that way there aren't questions in the future. But understanding a graph schema is a very complex process, and definitely not the type of thing that you're going to nail on your first shot. So I just really wanted to try and drive home some of the thought processes and ideas that you should be keeping in your mind when designing a particular schema. So thank you all very much for your time. And I hope that you learned something. And like I said, here's the list with all of the links. I'm going to drop this link back in the chat again. Oh, there it is. Thank you, Kelly. So feel free to go through this. Like I said, the notebook is essentially everything I talked about, just described in actual words. So if you don't want to have to watch a recording of this presentation or something, I highly recommend you go through the notebook and follow along with how everything is laid out there. So thank you again, everyone, for attending. Sorry for taking up a little bit extra of your time, but I hope that you learned something and that you're feel excited to try and tackle your first relational data set and get it converted into something that you can load into TigerGraph. And in 2 weeks from now, we will be looking at how we actually load in this whole monster of a data set with this absolute beast of a schema that we just created into a live running TigerGraph instance. And we take a look at what replicating the schema in TigerGraph looks like and getting our data mapped and loaded in looks like as well. So I hope that you're all looking forward to that, and I will see you in 2 weeks.